that we have some idea how to think about viscosity in terms of the relationship between stress and deformation, it's useful to kind of think more deeply about what exactly does this coefficient represent. Well, thinking back to our description, or at least qualitative description of viscosity in terms of the resistance to flow, we can imagine that this viscosity coefficient expresses interactions between fluid layers that can transfer momentum between them. So what kind of interactions can have this capability? Well, if you go back to our discussion about liquids, solids, and gases, remember that in the case of liquids, you have this situation where you have these weak cohesive interactions. So you can imagine that if you apply deformation to a liquid, these weak interactions will break, but they may locally continually break and reform during the course of the flow. And so this is exactly kind of a good way to think about the kinds of interactions that can be capable of transferring momentum between fluid layers, because at least for short periods of time when these interactions form, then momentum will be able to be transferred between different layers, between neighboring layers or neighboring molecules in the fluid. Another thing that we thought about in terms of gases mostly was this idea of random motion or interactions by collisions. So you could imagine that in a gas, you have these, this random component of the motion. So if a gas molecule from one layer comes into contact with a molecule in another layer, there's a collision, and then some energy or some momentum is transferred between those layers as a result of these collisions that continually take place between layers. So these kind of pictures are qualitative. They're useful to have in our heads to imagine what's going on, but they also do explain what we observe in terms of the temperature dependence of viscosity. So for liquids, we observe that as we increase the temperature, the viscosity goes down. And this makes sense because at high temperatures, these weak interactions between molecules will become even weaker because the thermal motion will become greater of the individual molecules. So that further acts against these weak cohesive interactions. And so a typical example is pancake syrup. You go to a restaurant that serves pancakes, and the syrup often is served heated up. And when the pancake syrup is heated up, it flows very easily, almost like water. So that's an example of this kind of property. As you increase the temperature, the viscosity goes down because these interactions, these cohesive interactions between molecules in a liquid become weaker. In a gas, that's kind of more representative of the second case. So gases, the molecules are interacting more by collisions. So for gases, we observe that the viscosity increases as the temperature increases. And this makes sense because as you increase the temperature, remember that's a representation of the internal energy of the system. So you would expect to have more collisions and more energetic collisions as you increase the temperature, so that there would be more opportunity or more capacity to transfer momentum between different layers of the fluid. And that's what's observed as the viscosity goes up with temperature for gases. So liquids and gases actually show opposite behavior in general with opposite dependence on temperature. And we can explain that based on these ideas about how individual atoms or molecules within the fluid would interact and be able to transfer momentum between layers. So this is what we mean really fundamentally when we're talking about viscosity.